Hello students, I am Sachitrakar. Welcome to GAUSS Physics. This is my lecture 16 on electrostatics and we are continuing electric charge and electric field. In previous lectures, we have discussed about Gauss law and some of applications of Gauss law. In this lecture, we will discuss another important application of Gauss law. That application is electric field intensity due to uniformly charged plane sheet. Okay, plane sheet. Sheet means a flat surface. Okay, this is a sheet, plane sheet. Okay, means when we consider plane sheet, then the thickness of the sheet, we do consider the thickness is very small. Okay, just it's a flat sheet, means a paper like substance. Okay, then the sheet is uniformly charged, charge given to the sheet. Okay, since the sheet has only surface area, charge can't be injected into inside of it. Okay, if charge is given to this sheet, the charge will be distributed on the surface of the sheet. Okay, let's consider this is a flat sheet PQRS. Of course, we have to consider this sheet is of infinite surface area. Okay, our consideration is like that. The sheet is of infinite surface area. Okay, charge is distributed on the surface. Okay, suppose this is a sheet which is given charge and charge is uniformly distributed on the sheet. Okay, charge is uniformly distributed on the surface of the sheet. Say students, suppose this is the plane sheet. This sheet is given some charge. I am holding the sheet like this. This is plane of the whiteboard. Okay, this is plane of the sheet. Now I do hold the sheet like this. Means the plane of sheet is perpendicular to the plane of whiteboard. Surface of sheet or plane surface of sheet is perpendicular to the plane or the surface of whiteboard. Okay, now this sheet is charged. Okay, if charge is given to the sheet, charge is distributed on the surface of sheet. Okay, since I am writing here the sheet is, we do consider like this, the sheet is infinite extent and of plane surface. Okay, the sheet is infinite extent and of plane surface. Again, charge is distributed on the surface. Suppose we have given positive charge to the surface. Okay, if charge is positive, then obviously electric field is in outward direction. Okay, since distribution of charge is uniform, so we may write the electric field is uniform and perpendicular to the plane sheet. Okay, electric field is uniform since distribution of charge is uniform. Okay, again electric field is perpendicular to the surface or the plane sheet, surface of the plane sheet. Okay, we have given positive charge. If positive charge is given, then electric field is uniform, perpendicular and away from the surface. If the charge were negative, then electric field would be perpendicular and uniform again towards the surface. positive charge, electric field away from surface, negatively charged, electric field is towards the surface. We have taken positive charge. Okay, then electric field is away from the surface. Okay, since the flat sheet has two surfaces, so electric field will be in both directions. Okay, suppose we have taken, let's consider this is x-axis, this is positive direction, and this is negative direction, x-axis dash. Then electric field will be uniform and perpendicular to the surface, and along this direction means along positive x-axis direction, and here along negative x-axis direction. Okay, let's consider our first step. Okay, to apply Gauss law, our first step is to consider a Gaussian surface. Okay, let's consider an elemental area dA at a distance r from the surface of the plane sheet. At a distance r from the surface of plane sheet, we do consider an elemental area dA. Again, at same distance r, we have considered again an elemental area dA. Okay, then total length 2r. Okay, just we may imagine the Gaussian surface is in the form of a cylinder of length 2r. Okay, of length 2r. Then first we do consider Gaussian surface, then we have to find flux by using general formula. Okay, so if this is positively charged and this is the elemental area, as we know, direction of area is perpendicular to the surface. See students, this is surface area of dA means elemental area. So direction of this elemental area will be in outward direction. This is direction of elemental area. Okay, also this is direction of electric field. Electric field is outward direction, also perpendicular to the surface. Okay, again this is also area, elemental area. Okay, this elemental area is along negative x-axis direction dA. Also electric field is perpendicular to the surface area. Okay, so let's take, this is elemental area P, this is elemental area Q, sorry, this is M, this is N. Okay, let the surface of this cylindrical Gaussian surface is, let's take O. Okay, so we have considered three surface areas at M, at N and at O. Okay, at M, electric field and elemental area are in same direction, so I may write here angle between electric field and elemental area is 0 degree. Okay, here also the same thing. At N means here the elemental area is dA, direction of dA and direction of electric field are in same direction. Here also angle between electric field and area, elemental area is also 0 degree. Okay, so here theta is 0 degree and here also theta is 0 degree. Okay, but if we consider the curved surface of cylindrical Gaussian surface, okay, cylindrical Gaussian surface, this is the curved surface. Okay, then here electric field is perpendicular to the plane sheet. Electric field suppose along positive x-axis direction here or along negative x-axis, but if you take an elemental area on this curved surface of the cylinder, then direction of elemental area is perpendicular to the surface. This is dA and this is direction of electric field, means electric field is perpendicular to the surface of flat sheet. So here theta is angle, means at O, angle between electric field and dA means theta is 90 degree. This is at O, this is at M and this is at N. Okay, thus to get flux, electric flux at M. M means here M is taken here where an elemental area is dA. Okay, so electric flux at M, flux surface integral of E dot dA, and this is equals to surface integral of E dA cos 0 degree, since at M angle between electric field and elemental area vector is 0 degree. So cos 0. So flux is surface integral of E dA. Okay, then electric flux at M. Here also angle between electric field and elemental area vector is 0 degree. Again, the same formula, flux is surface integral of E dA, because here also angle between electric field and elemental area vector is 0 degree. Then electric flux on the curved surface at O. Okay, O is taken. The O is the elemental area dA on this curved surface of cylindrical Gaussian surface. Okay, so here theta is 90 degree at O. Elemental area dA is direction of dA is, I am showing you, direction of dA is parallel. See, this is the cylindrical Gaussian surface and this is the direction of elemental area vector parallel to this flat sheet, and electric field is perpendicular to flat sheet. Okay, so here theta is 90 degree and flux surface integral of E dot dA cos 90. So here flux is 0. Then total flux let's take phi E, total flux, this is or phi, this is phi 1, this is phi 2 and this is phi 3. Then phi 1 plus phi 2 plus this is phi 3 is 0 at O. Then total flux is, this is phi 1 surface integral of E dA plus phi 2, again surface integral of E dA, again phi 3 is 0. Then total flux is 2 into surface integral of E dA, and which comes 2E. Surface integral of dA is A. So we get total flux, I am writing here, total flux phi is 2E A. Again check at point M, elemental area is dA, angle between electric field and dA is 0 degree. So flux is surface integral of E dA cos 0. So phi 1 is flux at M. So that's equals to surface integral of E dA, and that also same at M. Elemental area is at M. Here also angle between electric field and elemental area vector is 0 degree. Again phi 2 means flux at this elemental surface D is also surface integral of E dA, but flux at O means on the curved surface. If elemental area is taken on the curved surface, then this is direction of elemental area vector and this is direction of electric field. Then here theta is 90 degree and flux is 0. This is total flux. Flux is scalar quantity. So total flux is the algebraic sum of flux at M, at N and at O. Then total flux is 2A. I have written here. Okay. You may take screenshot for all these points. I have already taken the formula for total flux. Okay. 1, 2, 3. Okay, I am erasing. We have got the total flux. I am writing all this. So our aim is to get electric field intensity due to uniformly charged plane sheet. Okay, so plane sheet, uniformly charged flat sheet or plane sheet, we may take non-conducting sheet or we may take conducting sheet, but this is formula for total flux, may be conducting or may be non-conducting. If we consider first a non-conducting sheet, non-conducting uniformly charged plane sheet. Okay, so non-conducting sheet, suppose this is a sheet of non-conducting material. Okay, non-conducting, if charge is given to a non-conducting sheet, I am writing here, if charge is given to, okay, as we have discussed, the plane sheet or flat sheet has only surface areas. This is one surface area and this is also another surface area. So we will give charge to the surface. Charge can't be injected inside of the surface because the thickness is considered to be very small. Okay, so if charge is given to one of its surface, if charge is given to one of the surface of non-conducting sheet, then the charge will be localized and confined on that surface only. If charge is given to a non-conducting sheet to one of the surface, okay, to one of the surface, then since it is non-conducting, charge will be localized on the surface and be confined on one surface only. Okay, so distribution of charge will be uniform as we have considered, but the distribution of charge will on one surface only, but the opposite face means the opposite surface, charge can't flow through opposite surface. Okay, charge will be confined on one surface only. Then, as we know, according to GAUSS, okay, flux is 1 by epsilon naught times of the charge enclosed. Okay, another consideration I am writing here, this is formula for total flux. Let sigma is uniform surface charge density. Charge is given to the surface and charge is distributed uniformly. We do assume sigma is uniform surface charge density, means sigma is charge ratio of total charge to total surface area. Okay, total charge to total surface area. Then let charge given is Q, but charge is confined on one surface only. Let surface area is A. Okay, then sigma is equal to Q by A, then flux. Flux is equal to 1 by epsilon naught times of the charge. Here charge is sigma into A. Okay, this is equation 2. And total flux. Can I erase this? We have already discussed about this. Okay, then total flux. Total flux we have already taken. Total flux phi is equal to 2EA. Let's take it equation 1. And according to GAUSS, means applying GAUSS law, we get total flux is 1 by epsilon naught times of the charge, again in place of charge, charge is equal to the product of uniform surface charge density and one surface area of non-conducting flat sheet or plane sheet. This is equation 1. This is equation 2. Now equating equations 1 and 2, 2EA is equal to 1 by epsilon naught times of sigma into A get cancelled, then electric field is sigma divided by 2 epsilon naught. This is for non-conducting sheet. Plane sheet, non-conducting plane sheet, of course it is uniformly charged. Okay, so for non-conducting flat sheet which is uniformly charged, charge density is sigma, then electric field is sigma divided by 2 epsilon naught. Okay, of course as we have discussed in previous lectures, electric field depends upon distance. Okay, here we have taken distance on both sides r and r. Okay, but electric field is independent of distance. For uniformly charged plane sheet, electric field is independent of distance. Okay, this is about non-conducting sheet. Number 2, I have written the formula for electric field in case of non-conducting sheet. Number 2, for conducting sheet. Again the same assumption, conducting sheet is uniformly charged, flat sheet or plane sheet. Okay, suppose this is a conducting sheet. Charge is given to the conducting sheet to one of its surface. Okay, I am writing here. If charge is given to one of surface of conducting sheet, then the charge will not be localized, because this is conducting sheet. Charge will not be localized and not be confined on one surface. Okay, for conducting sheet, charge will not be localized, not be confined on one surface. Okay, not be confined on one surface, but distributed on both the surfaces. Okay, distributed on both the surfaces. This is the difference between conducting and non-conducting. For non-conducting sheet, charge is confined on one surface, but for conducting sheet, charge is distributed on both the surface, though charge is given to one surface. Okay, but electric field will be on both sides. So total flux, as per our general formula, flux is surface integral of electric field, that area vector. We have got total flux. Total flux is phi 2EA. This is equation 1. Okay, this is equation 1 for both the cases. But for conducting sheet, again according to Gauss law, flux is 1 by epsilon naught times of the charge enclosed. Again, uniform surface charge density is ratio of total charge to total surface area. But here for conducting sheet, total area is 2A, because if magnitude of one surface area is A, then charge is distributed on both the surfaces. The total surface area is 2A. So for conducting sheet, in this case we may write flux is 1 by epsilon naught times of the charge. Here charge is sigma into 2A. Sigma into 2A. This is equation 2. This is equation 1. Then I am solving here for conducting sheet. For conducting sheet, total flux phi is equal to 2EA. This is equation 1. Again, by applying Gauss law, total flux is 1 by epsilon naught times of sigma into 2A. This is equation 2. Now equating equation 1 and 2, 2EA is equal to 1 by epsilon naught times sigma into 2A. Okay, 2A 2a get cancelled, then electric field is sigma divided by epsilon naught. This is for conducting sheet. So for non-conducting sheet, electric field is sigma divided by 2 epsilon naught. For conducting sheet, electric field is sigma divided by epsilon naught. Okay, this is about electric field intensity due to uniformly charged plane sheet. For conducting sheet, electric field is sigma divided by epsilon naught. For non-conducting sheet, electric field is sigma divided by 2 epsilon naught. In both cases, as we observe, electric field is independent of distance. Okay, here sigma is uniform surface charge density. We have taken positive charge, so sigma is positive. You may take, if charge is negative, then charge density is negative. Okay, then one application question on the basis of this theory. Okay, can I erase all this? Only remember these two formula, and this is derivation for your board based question. Okay, a theoretical discussion on the basis of this application of GAUSS law. Okay, suppose we have taken two flat sheets, non-conducting sheets. Two flat non-conducting sheets kept parallel to each other. Okay, each flat sheet has area A. Let both are positively charged, uniformly charged distribution there. Let charge density is sigma 1 for this plate and charge density is sigma 2 for this plate. Okay, let this plate is P and this plate is Q. Both are non-conducting flat sheets. Okay, charge densities are sigma 1 and sigma 2. We have to find resultant electric field at three regions in this region. Region 1, this is region 2, in between the plates region 3. At these three regions we have to find electric field. Okay, this is the symmetric line. Okay, similarly we do consider elemental area here. Let this is M, elemental area is dA. Here also elemental area is dA. Okay, as we have considered here, electric field and elemental area vector are in same direction. Here also electric field and elemental area vector are in same direction. So here angle between A and dA is 0 degree. Here angle between A and dA is also 0 degree. Okay, then here electric field, we may take directly electric field. Okay, this is one plate, this is another plate. Okay, we know all these things, we know, and the direction of electric field for positive is away from the surface. We know all these things, just I am doing the representation of electric field. Okay, this is the line which is symmetric for both the plates. So here electric field due to this plate flat sheet P A1 away from the surface, and for this flat sheet Q electric field is let E2. Okay, so here also for sigma 1 means for flat sheet positively charged sheet P, electric field is along this direction E1, and for flat sheet Q which is also positively charged, electric field is outward, then electric field is E2. But in between, electric field due to this positively charged plate P is away from the surface. This is E1. For this positively charged plate, means for Q, electric field is outward. So here, electric fields are in opposite direction. So here, angle between electric field due to the flat sheet P and Q are in same direction. Theta is 0 degree. Here also, angle between E1 and E2 are in same direction. Theta is 0 degree. Here, angle between electric fields is 180 degrees since E1 and E2 are in opposite direction. So here, theta is 180 degree, and we know electric field intensity is a vector quantity. Okay. Then about direction. See, this is along positive x-axis, this is along negative x-axis. We may take sign convention. For positive x-axis, we may take sign positive. For negative x-axis, we may take sign negative. Then for region 1, E1 and E2 are in same direction. So angle between two electric field intensities is 0. So resultant electric field means magnitude of resultant electric field is magnitude of E1 plus magnitude of E2, and direction is along positive x-axis. Okay. Then electric field E1 sigma divided by 2 epsilon naught, electric field E2 sigma divided by 2 epsilon naught. Okay. Then resulting electric field is 1 divided by 2 epsilon naught. This is sigma 1, this is sigma 2. Okay. For E1 sigma 1, for E2 sigma 2. Charge densities are different. Okay. So sum of charge density sigma 1 and sigma 2. This is for region 1. For region 2, here also angle between E1 and E2 is 0 degree, but E1 and E2 both are along negative x-axis. So resulting means magnitude of resulting electric field is minus into magnitude of E1 plus magnitude of E2. Both are in negative x-axis. So sum minus E1 minus E2. So minus E1 magnitude plus E2 magnitude. So magnitude of resulting electric field is minus sigma by 2 epsilon naught plus sigma by 2 epsilon naught. Okay. So finally we may write minus 1 by 2 epsilon naught. This is sigma 1, this is sigma 2. Sigma 1 plus sigma 2. Okay. Then for region 3, I am doing here. For region 3, angle is 180 degree. If we assume sigma 1 is greater than sigma 2, then magnitude of E1 is greater than magnitude of E2. Since electric field is sigma divided by 2 epsilon naught for non-conducting sheet, if sigma 1 is greater than sigma 2, then magnitude of electric field E1 is greater than that of magnitude of electric field E2. Again, angle between them is 180 degree. Then resulting electric field, two electric fields are in opposite direction. Then magnitude of resulting electric field is magnitude of E1 minus magnitude of E2. But E1 is along positive x-axis, E2 is along negative x-axis. Okay. Then E1 sigma divided by 2 epsilon naught minus E2. E2 we will take negative minus, we have taken only magnitude E2. Magnitude of E2 is sigma divided by 2 epsilon naught. This is sigma 1, this is sigma 2. So the result is 1 by 2 epsilon naught into sigma 1 minus sigma 2. Here we have already taken angle between them. So considering positive and negative direction, positive x-axis and negative x-axis direction, we have taken theta is 180 degree. So magnitude of resultant field intensity is E1 minus E2. If E1 is greater, then resulting direction is along E1. Okay. So this is about electric field intensity in region 1. In region 2 and in region 3. Okay. Then we may consider, I am writing here and erasing this, if sigma 1 is equal to sigma 2. If sigma 1 is equal to sigma 2, in this case, as we have got in region 1, in region 1, we will take let sigma 1 is equal to sigma 2 is equal to sigma, both are same. Then for region 1, magnitude of resultant electric field, sigma plus sigma 2 sigma divided by 2 epsilon naught, that's equals to sigma by epsilon naught. For region 2, electric field intensity, magnitude of resulting field intensity is minus 1 by 2 epsilon naught into sigma 1 plus sigma 2, means sigma plus sigma, this is 2 sigma. Then magnitude of resultant field intensity is minus 2 sigma divided by 2 epsilon naught, means minus sigma divided by epsilon naught. For region 3, I am writing here for region 3, magnitude of resulting field intensity is 1 by 2 epsilon naught into sigma 1 minus sigma 2, but sigma 1 is equal to sigma 2, we may take sigma minus sigma, so magnitude of resulting field intensity is 0 in region 3. Okay, of course you may consider sigma 1 is positive, means plate P or plane sheet P is positively charged, plane sheet Q is negatively charged. If Q is negatively charged, then take sigma 2 negative and put in all these equations for region 1, region 2 and region 3. Okay, so this is about lecture 16, electric field intensity due to uniformly charged plane sheet. Okay, thank you students, continue your support, thanks a lot.